This person is standing in the shade of a dense urban canopy, but a harsh beam of sunlight is still hitting his face from the side. It is arriving from the glass facade on the opposite side of the street. This surface is explicitly designed to prevent solar heat from entering the tower. But the rejected thermal energy does not simply vanish into nothingness. It is redirected to find a new destination in the urban environment. So where exactly did it go? Seeing a bright reflection on the pavement is not enough to understand this phenomenon. The real question is how much additional radiant energy this person's body is actually absorbing. This is an invisible transfer of thermal stress. It is an investigation into what happens when a building passes its thermal burden to the street. To understand what is happening here, we first need to look at the numbers. This requires separating visual glare from actual thermal impact. A study published in Sustainability in 2022 provides the experimental baseline we need. Researchers assessed the reflection of solar radiation from the facades of tall buildings down to the pedestrian level. They documented the critical difference between diffuse reflection, which scatters light, and specular reflection, which acts like a mirror. The data revealed that reflected solar radiation can significantly increase the total thermal load hitting a target area. It is important to state clearly that this is an experimental result, not a direct field measurement of this specific Dubai street. We cannot take laboratory numbers and overlay them onto a random intersection, but this peer-reviewed experiment provides the exact physical mechanism our investigation needs to track. It confirms that the optical properties of modern building envelopes can double the solar irradiation experienced by a pedestrian. The light is not just bright. It carries measurable, quantifiable thermal power. The experiment proves that energy rejected by a building does not disperse evenly. It travels in straight lines until it strikes another surface. So why does a person standing in this zone of reflection suddenly feel so much hotter? The answer lies in understanding that a standard weather thermometer does not tell the whole story of human heat stress. Air temperature is only one variable in a highly complex equation that dictates how your body experiences the environment. Imagine two people standing on the exact same street, breathing the exact same hot air. The first person is standing under a solid concrete canopy. The second person is standing in an area receiving direct specular reflection from a nearby glass tower. If you hold a thermometer next to each of them, the air temperature readings will be almost identical, but the thermal balance of their bodies will be drastically different. The second person is being subjected to intense shortwave radiation bouncing off the facade. This radiation bypasses the air entirely and transfers its energy directly into their skin and the pavement beneath their feet. The pavement then absorbs this energy, heats up, and emits long-wave thermal radiation back up at their body. Have you ever walked through a patch of light so intense that your biological instinct forced you to turn your face away? That is your nervous system detecting a localized spike in radiant heat. Your body is essentially trying to maintain its core temperature by managing sweat evaporation. But when intense reflected radiation is added to an already hot environment, the physiological threshold for comfort is crossed instantly. The human body becomes a receiver for the energy the building refused to absorb. A slight difference in the geometry of the facade determines whether the incoming light is safely scattered or dangerously concentrated. To track the path of this rejected energy, we have to look at the shape of the surface rejecting it. It comes down to three basic geometric profiles and three very different physical outcomes. When sunlight hits a perfectly flat reflective surface, the light is simply redirected. The angle of incidence equals the angle of reflection. This can cause severe visual glare or cast a hot spot onto a neighboring building, but it generally does not magnify the energy. When sunlight hits a convex surface, one that curves outward, the reflected rays diverge. The solar energy is scattered across a much wider area, diluting its thermal impact on any single point. But when sunlight strikes a concave surface, one that curves inward, the physics change dramatically. A concave reflective facade acts as a parabolic reflector. It takes multiple incoming parallel rays of sunlight and forces them to cross paths. If the geometry is just right, These rays will converge at a specific focal point. At this point, the solar radiation is not just redirected. It is concentrated, multiplied, and intensified. But a concave shape alone does not automatically create a dangerous urban hazard. It requires a perfect alignment of specific factors. The orientation of the building must directly face the sun at specific times of the day or year. And most importantly, the focal point must physically intersect with a space occupied by human beings. Now that we know the precise geometric fingerprint to look for, we can take this physics lesson back to the streets of the city. Because a reflection only becomes a problem when it hits the right place at the exact wrong time. Our investigation returns to the urban fabric of Dubai, tracking the actual movement of these light patches. When evaluating a specific location, the visual evidence can be striking, but it requires systematic architectural analysis. We have to examine the geometry of the facade in question. Even a seemingly flat facade can behave unpredictably if the individual glass panels warp slightly under thermal expansion. Next, we must verify the exact orientation of the building. Which cardinal direction does the primary glass elevation face, and at what specific hours does it receive direct sunlight? Does the glass feature a highly specular metallic coating, or is it treated with a ceramic frit to encourage diffuse reflection? The answers to these questions determine the potential intensity of the reflected beam, but the most crucial element of this investigation is the receiving zone. Where does the light actually land? Is it harmlessly dispersed across open water, or does it strike a busy pedestrian sidewalk or the balconies of a neighboring residential complex? What immediately caught my attention during this analysis was not just the raw brightness of the reflection. It was the fact that the zone of impact is never stationary. Because the Earth is constantly rotating, the angle of the sun is always changing. This means the reflected focal point is in continuous motion. It drags across the pavement, climbs up the sides of adjacent structures, and sweeps through public spaces. This constant movement makes the phenomenon incredibly difficult to pin down. We can clearly see where the light travels and identify the architectural geometry that creates it. But relying on visual observation alone is the exact point where a serious investigation risks turning into clickbait. Seeing a bright light on a wall is simply not enough to declare it a systemic thermal crisis. We must separate dramatic visuals from verifiable thermal data. Without appropriate measurements or rigorous computer modeling, every striking video clip remains nothing more than a visually compelling hypothesis. To prove that a reflection is causing actual thermal stress, we would need to deploy precise parameters to measure the exact irradiance. We would need to log the data at the exact moment the focal point passes over the sensor. We would have to account for the background radiation emitting from the surrounding hot asphalt. And we would need to do this across different seasons, as the shifting solar altitude drastically alters the path of the reflection. Currently, for the specific Dubai locations being analyzed, we are relying on simulated scenarios and optical geometry. We are mapping the potential pathways of the light based on the built environment. This is a crucial editorial distinction. It would be easy to overlay a red thermal graphic onto this footage and claim the city is melting, but that would be intellectually dishonest. The available public data suggests that these specific locations are highly susceptible to concentrated solar reflection. They absolutely warrant rigorous on-site thermal testing by urban planners, but based on the current threshold of evidence, we cannot definitively label this specific street as a dangerous hotspot. Acknowledging this limitation is not a failure of the investigation. It is a necessary commitment to accuracy. We know the physics are real. We know the geometry exists. We just need to look at an international precedent to see what happens when all these factors align perfectly. To prove that this mechanism can yield severe real-world consequences, we must briefly look outside the Middle East. In 2013, a specific commercial skyscraper in London demonstrated the extreme limits of concave reflective architecture. The building featured a distinct, top-heavy curved profile facing directly south. During a specific period in late summer, the sun reached an altitude that perfectly aligned with the curvature of the glass. The facade acted as a massive parabolic mirror, focusing intense solar radiation onto a small stretch of East Cheap Street below. I am using this case study strictly to validate the physical mechanism of solar convergence. This is London, not Dubai. I am not claiming that this exact level of localized destruction has occurred in the UAE, but the London incident forced the global architectural community to confront a reality that had previously been ignored. It proved that a building's thermal footprint extends far beyond its physical foundations. Following the incident, the building required a permanent retrofit, installing a massive system of horizontal sunshades to scatter the light. At this point in the investigation, reflective glass seems like an obvious, undeniable villain in urban design. It appears to be a reckless architectural choice that prioritizes aesthetic sleekness over public safety. But arriving at that conclusion is entirely too easy. It completely ignores the fundamental reason why this material is used in the first place. We have to introduce a strong, fair counter-argument to understand the whole system. Reflective solar control glass was not invented to cause chaos on the streets. It was engineered to solve a massive, existential problem in modern architecture, particularly in desert climates. A glass skyscraper in Dubai is essentially a greenhouse trying to survive in one of the most intense solar environments on the planet. If architects used standard, clear glass, the amount of shortwave radiation pouring into the interior spaces would be catastrophic. To combat this, the glass is treated with microscopic metallic coatings. These coatings are designed to transmit visible light so people can see outside, while simultaneously reflecting the infrared spectrum that carries thermal energy. It lowers energy consumption, decreases operational carbon emissions, and meets the strict thermal transmittance requirements set by the Dubai Green Building System. These regulations demand high-performance building envelopes to ensure sustainability. It would be profoundly unfair to label all reflective glass as an architectural mistake. In a hot climate, preventing solar energy from penetrating the building is a genuine, undeniable engineering necessity. Perhaps the occasional bright reflection on a sidewalk is just a small, acceptable price to pay to keep thousands of indoor rooms habitable. That logic seems perfectly sound, and it justifies the widespread use of the material. But that mathematical equation only works if the boundary of the problem stops at the surface of the glass. This is where the entire concept of building performance undergoes a massive reversal. A high-performance facade operates exactly as specified by the manufacturer. It successfully rejects 50 or 60% of the incoming solar heat gain. It passes all the mandatory sustainability tests, secures the necessary green certifications, and proves that the tower is energy efficient. But physics dictates that energy cannot be destroyed. The heat that was mathematically subtracted from the interior of the tower was physically added to the exterior environment. A building can essentially achieve its own energy efficiency goals by shifting a portion of its thermal burden onto someone else. This creates a profound disconnect between performance at the building scale and comfort at the neighborhood scale. Solar energy does not respect property lines. Consider the perspective of a pedestrian trying to navigate the sidewalk, suddenly forced to walk through a localized zone of intense radiant heat. Consider the residents living in a lower, older apartment building across the street. Suddenly, their own air conditioning has to work harder to fight off the rejected heat of their wealthier neighbor. Would you call a structure truly sustainable if it consumes less power internally, but actively weaponizes sunlight against the public spaces surrounding it? This is not a malicious act by the architects. It is a blind spot in how we measure success. We calculate the energy saved inside, but we rarely calculate the energy dumped outside. And if this zone of reflection only exists for a brief window of time each day, there is a very high probability that standard assessment procedures will never even see it. To understand why this phenomenon is so frequently missed, we have to follow the trajectory of the light across a single day. There is no such thing as a stationary beam of heat. It is a dynamic entity, its path entirely authored by the rotation of the Earth, the orientation of the street, and the precise angle of every individual glass panel. By the late afternoon, as the sun descends in the west, the angles become shallow again, sweeping across pedestrian walkways and outdoor transit shelters. The critical detail here is duration. Because the sun is constantly moving, a specific focal point of intense heat might only linger on a particular balcony for 20 or 30 minutes. It arrives, it heats the surface, it causes severe discomfort, and then it quietly moves on. It leaves no permanent physical trace behind. If an urban planner or a building inspector visits the site at 10 in the morning, they will document perfectly normal conditions. If the reflection peaks at 2 in the afternoon, the morning inspection will completely miss the event. A phenomenon that only exists for half an hour is incredibly easy to overlook if you are not running a highly granular, time-based simulation. We know what shapes cause it, and we know how it moves. The question is whether the regulatory frameworks governing these massive developments are actively looking for it. This brings our investigation to the intersection of building physics and design accountability. When a new glass tower is proposed, the engineering teams submit extensive documentation detailing the performance of the building envelope. They report the thermal transmittance, the shading coefficient, and the visible light transmittance. They prove that the cooling loads are optimized. But we have to ask, what is missing from those spreadsheets? Is there a mandatory requirement to simulate the specific path of reflected light onto the opposing buildings? Are there strict thresholds for solar glare on adjacent traffic arteries? Is the radiant heat increase measured specifically at the pedestrian level rather than just at the roof? Are they required to run simulations that account for every month of the year to catch those brief windows of convergence? Some international jurisdictions, like the City of London Corporation, have implemented specific planning advice to assess the microclimatic impact of tall buildings. They recognized that a cluster of highly reflective facades changes the urban environment. I am not claiming that Dubai entirely ignores these factors, as urban planning guidelines are constantly evolving. But in my view, the largest blind spot in modern architecture does not necessarily lie in a specific type of glass. It lies exactly where we decide to conclude our calculations. If the simulation stops at the outer pane of glass, everything looks perfect. But thermal energy does not stop simply because the property boundary on the architectural blueprint has ended. The encouraging reality is that resolving this issue does not require humanity to abandon glass architecture. The technological and design solutions are entirely within our reach. The first line of defense is geometry. Architects can actively avoid designing large, unbroken concave curves that face the sun. If a curved aesthetic is required, the surface can be broken into smaller, faceted panels that scatter the light, rather than focusing it. Extensive sun path simulations must be run and verified before the final facade geometry is locked in. The second solution involves material science. Instead of relying on highly specular, mirror-like finishes, designers can utilize glass with a higher degree of diffuse reflectivity. Applying a ceramic frit pattern to the glass can effectively break up the reflection, ensuring that the rejected energy is scattered harmlessly. Third, the use of external shading devices can intercept the sunlight before it ever reaches the reflective glass. Fourth, if a reflection cannot be completely designed out of the building, the receiving space must be protected. Pedestrian walkways can be covered with heavy shade structures. Finally, there must be a commitment to post-occupancy evaluation. We must test the buildings after they are built, verifying that the models match reality, and taking the thermal complaints of the surrounding community seriously. The engineering knowledge is already here. The deciding factor is simply whether the final calculation is performed for the benefit of a single building or for the entire street. As the late afternoon transitions into evening, the sharp patch of light finally slides off the pavement. It sweeps upward, momentarily illuminating the side of a concrete wall, before fading away completely as the sun dips below the horizon. The street returns to normal. But the physical energy that struck the ground did not simply disappear. It was merely transferred. It left the building that refused to absorb it, and it arrived in a public space that was never given a choice in the design process. The ultimate question posed by this investigation is not whether a desert city should stop building with glass. The question is much more fundamental. It is whether a piece of architecture can truly be considered efficient when its mathematical success ends exactly where the daily lives of other people begin. This video is an independent architectural investigation intended for educational purposes. The analysis of solar reflection and thermal dynamics relies on available scientific research, optical physics, and environmental modeling. Visual representations may include simulated scenarios to explain physical mechanisms and do not represent verified field measurements unless explicitly stated. If you found this investigation into the hidden thermal systems of our cities valuable, consider subscribing to the channel. How should cities regulate the heat rejected by modern buildings? Share your perspective in the comments below.